In this video, we're going to talk about the reactions of alkynes. And these are the essential reactions that you need to know. So the first reaction we want to talk about is hydrogenation. We're just adding hydrogen. Now, if you have a alkyne like this, right, 4 carbons. If you have an alkyne like this and you add H2 and platinum, right, you'll get something that looks like this. You get an alkane. So you notice it reduces the triple bond all the way to now an alkane, right? You only have single bonds. So we need a way to control this reaction. So the first one you want to learn under hydrogenation, all right, is the idea of taking this molecule and adding hydrogen gas in some sort of catalyst. Usually it's a large catalyst, and it's basically a poison catalyst, or sometimes you'll see poison cat. And the structure looks something like this. And the second half of the structure is kind of a complicated structure, so most times they write it as just cat, but it looks something like this for your curiosity. Has this amine group here, right? And you'll see this in palladium, barium sulfate. So this is Lin-Large catalyst, combination of things, right? So when you add this, it turns out that you get the cis alkene. So you'll get something that looks like this. You get the cis alkene. Notice that my 2 methyl groups are on the same side. My hydrogens are on the same side. So you get the cis alkene whenever you add H2 in the presence of a poison catalyst, right? In the reaction number 2 under this subcategory, you could actually take this molecule and add sodium in its elemental form in liquid ammonium. And this will give you the transalkene. So this will give you the cis. This will give you the transalkene. So you'll get something that looks like this. This will give you the transalkene. Notice that my hydrogens are now on the opposite side. So this is the transalkene. So sodium solid in liquid ammonia gives you the transalkene. So that's hydrogenation. The next one we want to look at is hydrohalogenation. All right. And now we're just I guess under the subcategory. All right. So under this subcategory, we have the addition of HX. Right. So under this category, we have the addition of HX, and this gives you the Markovnikov regional isomer. Right. So if you have a alkene like this, all right, and you add HBr, and there's something important that I forget to mention. Kind of put this in your toolbox. Let me mention it up here. We have terminal alkynes and we have internal. Most of the reactions we talk about will deal with internal alkynes, and it has the formula of this. Maybe we should put another carbon here where the carbon-carbon triple bond is in the middle. The carbon-carbon triple bond is in the middle. Right, the carbon-carbon triple bond is in the middle. With terminal, it's at the end, so you might see something like this. Notice that we have a hydrogen here at the end. So when we talk about alkyne reactions, we'll mostly be talking about terminal alkynes. Now you'll see internal alkynes when we talk about halogenation, but just keep this in mind. I forgot to mention it. So the addition of HX gives you the Markovnikov region isomer. So you're going to get something like this. Right. Notice that my bromine is now on the more substituted part of the carbon-carbon triple bond. Right. We have a hydrogen here, so this is less substituted. So this gives me the Markovnikov region isomer. The second one under this is you could also get the anti-Markovnikov region isomer. So to get the anti-Markovnikov, right? So you can get the Markovnikov and the anti-Markovnikov. So if you have the same molecule, now you could add HBr, HX with a peroxy acid, right? And so this typically is MCBPA. I always get it mixed up, but this is a peroxy acid again, right? And what this does is that it gives you the anti-Markovnikov regional isomer. So now you get the bromine being on the least substituted part of the carbon-carbon triple bond. All right, so this will be your product, and then obviously you have this hydrogen here, but this will be your product. All right, so we went through hydrogenation, and hydrohalogenation. All right, so the third one you want to familiarize yourself with is hydration. And hydration implies water, right? And there's two subcategories under this one. All right, so the first one, we use this reactant. So what if we have the same molecule? We're gonna add mercury acetate in the presence of sodium borohydride in the second step, and this will give you this product. It will give you an alkene, right, with the alcohol being on the more substituted part of the carbon-carbon triple bond, right? So this is what you'll get, and obviously the H goes right here, right? But actually this is not what you get, and put in parentheses this. In organic chemistry, we call this an enol. This is a functional group. We call this an enol, right? Anytime you have an alcohol beside a carbon-carbon double bond, this is called an enol. And so this is actually an intermediate. And what happens in the reaction, it turns out that the former ketone is much more stable. So this hydrogen from the oxygen comes and kind of rotate around that carbon, and the double bond kind of pushes up. All right, so the actual product you'll get is something that looks like this. Right, with the extra two H's. Right, and this will be the product. Now this is a ketone. So whenever you're adding water to an alkyne, to alkynes, it will give you ketones when you use mercury acetate in the presence of sodium borohydride. Under the second one, it turns out that we could also do hydroboration, right? So if we take the same molecule and add BH3 in the presence of THF and sodium hydroxide, H2O2. In the second step, this is what you get as the intermediate. The OH is now on the less substituted part of the carbon-carbon double bond. All right, and again, this is an enol. This is actually an intermediate. So what happens is that this hydrogen comes, circle this carbon, and this double bond floats up. All right, and look what you get. No, this should not be a double bond here. All right, and we have these two hydrogens now kind of circulating this carbon. So this is what you get. You get an aldehyde. So again, adding mercury acetate in the presence of sodium borohydride, adding water, you'll get a ketone. When you add hydroboration, you get an aldehyde. All right, so that's hydration. The other one you need to familiarize yourself with is halogenation. And it's this idea of that if I were to take this molecule, you'll see something like bromine, Br2, in excess. All right, and all this does is that it adds 4 halogen across the carbon-carbon triple bond. All right, and this will be your observed product. So again, halogenation of alkynes. Usually you'll see Cl2 in excess. Any halogen in excess, well, it's just implying that you're adding 4 of those to kind of reduce that carbon-carbon triple bond to an alkane, with the halogens being doubled that of the alkenes. So that's just all for halogenation. And the fifth one, I'm sorry about that, is ozonolysis. And under this subcategory, we have 2 reactions. So it turns out that if you have a internal alkyne, you actually get two carboxylic acids, right? So for example, if you have something like this, all right, notice that this alkyne is internal. So if internal, you get 2 carboxylic acid. All right, so if you add O3, ozone, in the presence of NMO, right, you cleave this carbon-carbon double bond, and here's what you triple bond, and here's what you get. You get 1 carboxylic acid, and here's the other one. Let me kind of draw it well. There's my CH3. And there's my other my other carboxylic acid. So again, if the alkyne is internal, you get 2 carboxylic acid. All right. Now the second one, if it's terminal, right? So if you have something like this, right, and you were to add ozone in the presence of NMO, you'll get a carboxylic acid and CO2. So once you cleave this carbon-carbon triple bond, you get something to look like this. Right, so you get that carboxylic acid there, right, plus CO2. And that is if the alcohol, that is if your alkyne is terminal.